All right. So hello everybody. Yesterday we talked about time dilation, right? And again, this is something that takes a little bit of getting used to, but I hope that you have spent some time thinking about these concepts. They are not obvious results, so it helps to think about them. If it was obvious, then you wouldn't need to take a college class, right? I mean, it would be obvious, but it's not. And anything that is useful, any kind of knowledge that is useful is never obvious, right? It always takes some effort. So if you find that learning is when the learning process is frustrating or painful, if it's not frustrating and painful, then you're not learning. So that's the nature of learning, right? So of course, if it should be more than just frustrating and painful. If it's only frustrating and painful, then you're doing something wrong. But the frustration is a part of it, and if you're willing to face that, then at the end of the day, you will be rewarded, right? You'll be rewarded with understanding, and there is great joy in understanding, right? So, all right, so let's talk about length contraction today. And again, since you all remember that in past couple of sessions, we've had a lot of audio video disruptions. If there is any issue with the audio at any point in time or the video, you please unmute yourself and let me know right away, okay? Okay, so today we are going to talk about the complementary aspect of time dilation, which is length contraction. Okay, so contraction means to shrink, right? So what is the meaning of length contraction, right? It means basically the picture is the following, that you have some observer O. This observer has some object which in the observer's own rest frame has a length, proper length L naught, and then this observer is moving with some velocity v naught with respect to another observer, let's say outside the box, outside the train or the rocket ship or whatever it is, right? So O makes a measurement of the length of L naught, right? Now the question is, how do you make a measurement, right? This is important. In yesterday's lecture, when we talked about time dilation, when I derived it using this Lorentz contraction, right? So you have a clock that is in the O frame, and one important assumption that we made was that the clock stays at the same position in O's frame of reference, right? So the x coordinate, we are measuring time intervals. We are measuring the time interval between two space-time events. So the two space-time events are what do you call it? Okay, I numbered these incorrectly. Let me just fix that. X1, X2, right? So the two space-time events, well, I label them as T1 X1 and T2 X2, right? And then the time interval is T2 minus T1. But the important thing to keep in mind is that the x2 is equal to x1, which means the clock is not moving, right? It's at rest. If you are measuring a time interval, the position of the clock has to remain unchanged. In the same way, when you make a measurement of the position in the rest frame, right, both of the ends of the interval which you are measuring, both those ends should be on the same constant time surface, right? So we can understand this in terms of a space-time diagram where, so this is the O frame of reference, okay? And in this O frame, there is a rod that is placed so that its two ends, okay, lie at L0 by 2 comma 0 and minus L0 by 2 comma 0. These are the space-time coordinates of the two ends of the rod, okay? Now the question is, how does one make a measurement of length? Well, one way is that you put these flash bulbs, light bulbs at both ends, right? And you set these flash bulbs to go off simultaneously in the rest frame of O. Then what happens is these light bulbs emit light, right? And since they are placed equally far apart, what happens is when the light reaches this point, it will reach the center point at the same instant of time, right? So then what one does is you measure the amount of time it took this light to travel from here to here, right? You measure this time, delta t, right? And from this measurement, you can figure out that L0 by 2, right, is equal to C delta t. So L0 is equal to 2 times C delta t. Okay. So this is what it means to say that we are conducting a length measurement. All right. Okay. Now, okay. Now let's ask the same thing, same question. How are we going to measure this length as seen by O prime? Okay. Now let me go back to the space-time diagram picture. So in the space-time diagram, right? So this is a space-time diagram, and I have, so this, in this space-time diagram over here, let me copy and paste it. Yeah, it's less crowded. Okay, so this is the space-time diagram of the frame of reference of O prime, right? You can see that this is X prime and this is CT prime. So this is the frame of reference, the rest frame of O prime. Okay. Now with respect to O prime, O is moving with some velocity, V0 in the positive x direction, right? So how do we represent the motion, the trajectory of O in the frame of reference of O prime? We will represent it as a diagonal line, right, whose slope m is equal to 1 by beta, where beta is equal to V0 by C. And so this is also the same as the time axis. This is the, as seen by O prime, this is the trajectory of O, okay? but this axis is also the same as this time axis, right? This time axis that we have drawn here for the O frame of reference, right? This is if you get confused about this, think of a simpler picture that you do understand, which is the picture of rotations, right? Rotations in 2D space, right? So you consider some set of coordinates x and y, right? And then you perform a rotation to a different set of coordinates, okay? X prime and y prime, right? And this is a rotation by some angle theta, okay? Now you can look at the picture from the perspective of x prime and y prime, right? So this is the picture from the perspective of xy. This is the picture from the perspective of the prime frame, right? So in the prime frame, what do the x and y coordinates look like? Well, you can just reverse this diagram a little bit, right? And you can see that this looks like x and this looks like y. And then this angle, or this angle is theta, right? That's right. No, this angle is theta. So you're looking at the exact same picture, okay? Just from a different frame of reference. So when you draw, if I ask you what happens to the y-axis of the O frame in the O prime frame, right? Well, what happens to the y-axis? The y-axis becomes this diagonal line. What happens to the x-axis? The x-axis becomes this diagonal line, right? So in exactly the same way, when I look at two different observers in so I have one observer, which is O. In O's frame of reference, this is the axis, right? Now I can ask, right, that O is moving with respect to O prime, whose frame of reference is this x prime ct prime, right? Now, if this was just a spatial rotation, then the axes would just be rotated in this way, right? But this is not an ordinary spatial rotation. What is it? This is a hyperbolic rotation. But we can do the same thing. We can ask what happens to this axis as viewed from this perspective, right? So what is this axis? Again, this axis corresponds to this is a constant x surface, right? What is the equation of this line? The equation of this line is x is equal to 0, right? So I can ask what happens to this equation when seen from this frame of reference. Okay. So now if I make the Lorentz transformation from O to O prime, how do I do that? Well, sorry, I should probably put the primes on this one, right? I'll put the primes here and make this the unprimed one. Okay. Okay, yeah. So this is x prime is equal to 0. This is the O prime frame of reference. I ask how does this x prime equal to 0 look like in this frame of reference? So I perform the Lorentz transformation to go from the prime coordinates to the unprimed coordinates. What is the Lorentz transformation? X is equal to x prime right? Plus V naught T prime gamma, right? If you look at this picture, right, you can see that O is moving to the left. So you have to, with respect to O prime, so you get this plus sign over here. Okay. And what is T? Well, T is similarly V naught X prime by C squared times gamma. Right. Now all we need is this equation X prime. X prime is equal to 0. Right. So we write down, so what we need to do is write down X prime in terms of X and T. Well, that will just be the inverse of this transformation. So X prime is equal to X naught minus, sorry, X minus V naught T times gamma, and then T prime is equal to T minus V naught X by C squared gamma. Right. This is just the inverse transformation. So the velocity just changes sign. And now my equation is X prime is equal to 0. So if I set that equation to be true, right? So X prime is equal to 0 implies that this equation is 0, right? Which means that X is equal to V naught T. So this line, right, is mapped to a different line in this frame of reference. Which line is it mapped to? It is mapped to the line which satisfies this equation, X is equal to V naught T. What is this line? This line is simply the line, the trajectory of an observer moving with a velocity V naught, with m is equal to 1 by beta. Right? And this line is, so which is this line? This line is CT prime. Sorry, is there a question from somebody? Okay. So this line is CT prime. It's this observer's time axis, right? It is also the same as what this observer's trajectory looks like in this frame of reference. Okay, so let me extend this back. Okay, I'm not very good at this whole extending thing. Now let me draw the light this thing axis, right? The 45-degree line. So this is the 45-degree line. Okay. Now I can ask the exact same question about the x-axis. What happens to this x-axis? Okay. Now can somebody tell me what is the equation of this line? This line is what?
CT dash 0.
T
T dash is 0, sir.
T prime is 0, right?
T prime is 0.
T prime is 0. Now, so I translate that into this expression. So T prime is equal to 0 becomes this quantity T minus V naught X by C square gamma is equal to 0, right? Which means that T is equal to V naught X by C square. So CT is equal to V naught X, right? So this is the same expression as if I take, so what is the slope of this line? The slope of this line now is m is equal to CT by X. CT is the y coordinate, X is the X coordinate, right? So this is the slope of the line. And what is it? This slope is V naught, right?
Sir, CT is V naught X
Sir,
by C.
V naught by C, sorry, V naught by C. And what is this? This is equal to beta, right? And beta is less than 1. All right. So how do I draw the line corresponding to this x prime axis? I draw it as a line which has a slope m is equal to beta. Okay. So what happens to the coordinates of the x and y coordinates as seen by the other observer? They become pinched like this. And the faster the object is traveling, the more pinched they will become. So the faster O prime is traveling with respect to O, what will happen? This axis will become more and more closer to the diagonal, and this axis will become more and more closer to the diagonal. It's like you start out like this, and then it starts pinching in towards the 45-degree angle from both sides. This is the hyperbolic rotation. Okay. Now we want to talk about this length measurement. And how did we do this length measurement? We did this length measurement by placing this rod on the constant time surface. By placing this rod on this surface, right, over here. At L0 by 2 comma 0 and minus L0 by 2 comma 0, right? So these two ends of the rod, now I can ask, how does this rod look like as seen by O? Right?
Smaller rod, sir.
Well, I'm not smaller or larger, we'll see in a second. But for the time being, let me just look at how to draw it in this picture, right? Now, in this picture, the x prime axis is this line, right? So the rod lies on this line. Maybe I'll use a different color for the rod since I'm already using orange to depict the light curve. So I'll use red. So the rod appears to lie on this axis. Like this. This is the rod as seen by O, right? Okay. Now let's ask what is the length of this rod as measured by O. Okay. So how should O make a measurement of the length of this rod? So let us look at this Lorentz transformation again and ask what happens. 1 second. Okay, so let's derive the length as seen by O. Okay. So how did we determine the length as seen by O prime? We measured the location of the endpoints of the rod. We measured the locations of the endpoints of the rod at the same time with respect to O prime, right? So that means T1 prime is equal to T2 prime, right? And then we took X. So this coordinate we can say is x1 prime comma T1 prime, and this is x2 prime comma T2 prime, right? These coordinates give you the location of the endpoints of the rod. And so what is the length of the rod? T1 prime is equal to T2 prime. So the length is x1 prime minus x2 prime. Okay. So a length L naught is equal to x1 prime minus x2 prime. Okay. So now we transform to the other frame of reference, right? So when we transform to the other frame of reference, what do we get? We have to use this expression for x and t in terms of x prime and t prime. So I have this expression, right? So now what will be the location of the ends of the rod? The location of the ends of the rod as seen by O are at coordinates x1 comma t1 and at coordinate x2 comma t2, right? So I can ask what is x1 t1 and x2 t2 in terms of x1 prime and in terms of the prime coordinates. So what is this? x1 is equal to x1 prime plus v naught t1 prime, and we can set the initial time to be 0 just for convenience, right? Same thing, t1 prime is equal to t1 prime v naught by c square x1 prime gamma, right? Now t1 prime is equal to 0, right? So what do I get? I get x1 is equal to gamma x1 prime, right? And t1 is equal to v naught by c squared gamma x1 prime. All right. Then in the same way, for x2 and t2, I would have the same kind of equations, and I would get x2 is equal to gamma x2 prime and t2 is equal to v naught by c square gamma x2 prime. Okay. But we are not concerned with t1 and t2. We are concerned with x2 with only the x coordinates. So what is the length of this rod as measured by this observer? The length of the rod as measured by this observer is x1 minus x2. So this is x1, this is x1, and this is x2, and the length of the rod as measured by this observer is this distance, x1 minus x2, right? So what is this? x1 minus x2 is equal to gamma times x1 prime minus x2 prime. Okay. Which means that the length of the rod as measured by O is equal to, so what is this x1 prime minus x2 prime? x1 prime minus x2 prime is the length of the rod, proper length of the rod. So this becomes gamma times L naught. Right.
Sir, it is expansion, not contraction then.
Yeah, I know. For 8 years I've been teaching this course. Every time I get to length contraction, I make the same mistake. So well, if you look at this picture, you can see that
Sir,
this
here X
diagonal the length will be longer than the, yes,
in the Lorentz
yes,
transformation, we took
somebody
X dash
trying to
instead
say
of
something.
X, sir. Sir, this one. Here, in the Lorentz transformation, we took X
Your
dash
voice is
in
not
place of
clear.
X. But we took,
Venu Madhav, your voice is not clear. What are you saying?
sir, in the transformation of length, sir, we took X dash, sir, in terms of X. I mean, if we take X dash by gamma, we'll get no, sir. X is equal to X dash by gamma, X prime by gamma plus V naught T.
Which transformation?
Lorentz transformation, sir.
Which one?
Once told somewhat more, somewhere.
Here?
Still there. No, still here, sir. Here we took that X is equal to X dash plus V naught T by gamma, no, sir. And we need X dash is we are talking in terms of prime, no, sir. X prime, and we need that X prime, not X. Difference in X prime. Sir, did I get you?
One second. Let me think about this. Right. The time dilation part is always easy. The length contraction part is the one where I always get mixed up.
Sir,
Let me see
we
again.
took in terms of O prime, sir, but we calculated in terms of O, sir, so that's the way.
So this is O prime. This is the length of the rod. In the rest frame of the rod is L naught, is x2 prime minus x1 prime. Is that fine? Yes?
This is all fine, sir. We had done the wrong in the lower steps. I had done it in paper. I got that answer, so that.
Now, so in terms of O prime's frame of reference, the length of the rod should be x1 prime minus x2 prime, no? Oh, sorry, x1 minus x2, isn't that right? But then if you do that, that gives you gamma. So what is the logical? There's a logical error I'm making here. I don't know.
Sir, here that step C, sir. L naught is equal to x1 prime minus x2 prime here. But we had calculated x not x dash, not x prime. We had calculated x, no, sir, not x prime in this step. We know the difference between primes, but we had took the difference between x's.
So what should I be doing then? X2 prime minus x1 prime. Okay, look, if you just look at this picture, you can see that the length as measured by O is going to be less, right? So let me actually show a different picture that makes things a little bit clearer. Length. Okay, let me let me follow the derivation in crane instead, okay? Which doesn't involve all of this. So let me use that. All right. Okay. So fine. Let's look at this clock. Okay, it's the same picture, but now the clock is horizontal, and we have this clock. Okay, and this is the O prime frame of reference, and the clock emits the light in the direction of motion, and the length of this rod, as measured in O prime frame of reference is L naught. Fine. But now O prime is moving with respect to O. So what happens? When the beam of light starts out from this end, as seen by O, this is the location of the back end of this cylinder, this clock, and the length of this clock is L, as seen by O. Okay. Now let's say that this beam of light reaches the other end. So this end is A, this end is B. Let's say by the time the beam of light reaches the other end, okay, this beam of light has been emitted from A, it reaches the other end over here, and it takes an amount of time, which is delta t. Okay. Right. So in this amount of time, what is the total distance that the light travels? The light goes from here to here. All right. And what is this total distance? This is c times delta t1. This is the distance traveled by light, as seen by O. Okay. Now, what about the end of this box? The end of this box, the whole box is moving, right? The whole box is moving at a speed v naught with respect to O. So the end of this box, this portion, right? It goes from this location to this location. And what is this distance? This distance is v naught delta t1. Okay. So if I ask what is the sum of length L plus v naught delta t1, it is going to be equal to c delta t1. So I can write c times delta t1 is equal to L plus v naught delta t1. And again, remember, L is the length of the box as seen by O. Okay. Now we consider the journey of the light on the way back. Okay. So now we have the same box A and B. It's moving with some speed v naught in this direction. The light is emitted from B. Okay. Then the box moves forward, right? It moves forward by some distance. By the time this light beam reaches back to A, the box has moved forward some distance, right? It has moved forward by this distance. Okay. And what is this distance? Well, again, let's say that it takes a time delta t2 for the light to go from here to here as seen by O. So then this distance will be V naught delta T2. Okay. And then what can you say about this distance? What is the distance the light has actually traveled as seen by O? It is this distance, right? As seen by O, the light has gone from this position to this position. So that displacement is this amount. What is this amount? It is equal to the length of the box as seen by O minus this portion. So this is L minus V naught delta T2. Maybe I'll put this. This is L minus V naught delta T2, right? And this distance has been covered by the beam of light. So that means, what is that distance? It's equal to C times delta T2, and this is equal to L minus V naught delta T2. So finally, we have these two expressions. Delta T1 is the time it takes for light to go in the forward direction, and delta T2 is the time it takes the light to go in the reverse direction. Okay. Now now what do I do? Now I can solve both of these expressions for delta T1 and delta T2. So if I solve this expression for delta T2, what do I get? I get delta T2 times C plus V naught is equal to L, which implies that delta T2 is equal to L divided by V naught plus C. In the same way, delta T1 is equal to L divided by C minus V naught. Okay. So delta T1 is equal to L over C minus V naught. Delta T2 is equal to L over C plus V naught. What is the total sum of these two? Delta T1 plus delta T2, it's delta T. And if I take the sum of these two expressions, what do I get? I get L
2G divided by C square.
2L C over C square minus V naught square. I take C square common in the denominator, and I get 2L by C over 1 minus V naught square by C square. Right? So this is the total time it takes for light to travel, complete one cycle, complete one whole cycle as seen by O. Right? So delta T is equal to 2L by C, 1 minus V naught square by C square, as seen by O. Now you remember that in the rest frame of the clock, delta T prime is the time taken in the rest frame of the clock. Right? When we looked at the time derivation, the derivation of time dilation, rest frame of the clock. And what did we say about what did we find out about the relation between delta T prime and delta T? We found that delta T is equal to gamma delta T1. Right?
Yes, sir.
Okay. And what is delta T D prime? Delta T prime is 2L naught by C. So because this is the time it takes for the light to go to the left and to the right in the rest frame of the clock, right? So I get this expression for delta T. Now I have two different expressions for delta T. I have an expression here in terms of the length as seen by O, and I have an expression for delta T in terms of the length L naught as seen by O prime. And these expressions are equal to each other. So this means that 2L by C 1 minus V naught square by C square is equal to 2L naught by C root of 1 minus V naught square by C square. C 2 cancels, and I will end up with L is equal to L naught 1 minus V naught square by C square, which is equal to L naught by gamma. So the apparent length of the rod as seen by O is less than the length of the rod as seen in its own frame of reference. Okay, so this derivation is I think much easier to follow personally, but the only problem with this derivation is that it sort of relies on the time dilation result. So you might not like this fact too much, but anyway, yeah, it works out. And okay, now we can ask what are some applications of this length contraction. And by the way, again, if O sees this length contracted by an amount 1 by gamma, then what happens as seen by if I take the same rod and give it to O, and then O prime looks at it, O prime will see the other rod contracted, again by the relativity of motion. Okay.
Yes, sir.
So again, please keep that in mind whenever you look at such problems. Now we'll do a very simple numerical for this. Okay, and this is called this is related to the question of muon decay. So muons are elementary particles which are formed in the upper atmosphere of the Earth, and due to the collision of cosmic rays with the molecules in the atmosphere. Okay. Now, so this is example 2.4 in Crane, 2.4 and 2.5. So the muon is moving at some velocity, which is very large. It's in fact 0.99978 times c. This is example 2.5 in Kenneth Crane. Okay, this is the velocity of the muon. Now the distance between the Earth's surface and the upper atmosphere, where the cosmic rays collide with the atmosphere and the muons are formed, this distance is L naught is equal to 100 kilometers, approximately, give or take. And you have these muons which are moving down towards the Earth, right? So one can ask, what is the effective distance as seen by the muon, right? This 100-kilometer distance. So this 100-kilometer distance, you can imagine that, let's say that you can build a rod that is 100 kilometers long, and you place this rod vertically on the surface of the Earth, so that one end is on the surface of the Earth and the other end is touching the upper atmosphere. Then you ask, what is the length of this rod as seen by the muon, right? So the length of this rod as seen by the muon will be L naught by gamma, which is equal to 100 kilometers. Now what is gamma? So this is again it's important to understand how to calculate gamma for such quantities. So gamma is equal to 1 over root of 1 minus 0.99, right? And so on. Something 99978 C by C whole square. Okay. So this is really this is a really large number, right? How large is it going to be? When you divide 100 kilometers by this gamma, you will get so this will be approximately, this will be more than 100 actually. So when you divide 100 kilometers by this gamma, you get an answer which looks like this: 0.66 kilometers, which is equal to 660 meters. So the length of this rod, as seen by the muon, is actually 660 meters. Now the reason this is important is because muons are unstable particles. That means muons decay, okay? And in their own rest frame, the half-life of a muon, delta T, is equal to 2.2 microseconds. Okay? So that means at the time the muon is created in the upper atmosphere, it has 2.2 microseconds in its own rest frame, right? To reach the surface of the Earth. If it decays before that, then it will never reach the surface of the Earth, right? Now, what is the distance the muon perceives to be between itself and the Earth? It doesn't see the distance to be 100 kilometers, right? It sees the distance to be 660 meters. Okay? And now it is traveling at a speed V naught of 0.999978 C. So we can ask, what is the distance the muon is able to travel? What is the maximum distance the muon can travel before it decays, right? Before it vanishes. Well, that is equal to the speed of the muon multiplied by the lifetime of the muon. What is this going to be? This is, I can take V naught to be approximately C, right? Because this is so close to 1. So let me just take it as C. 3 times 10 to the 8 times 2.2 microseconds. Microseconds is 10 to the minus 6. So this gives me 6.6 times 10 to the 2 meters. What is this? This is 660 meters, right? So if the muon is traveling at this speed, the maximum distance the muon can go before it decays is 660 meters, right? So if you don't have relativity, what will happen? The muon will be created at the upper atmosphere. It will travel a distance of 660 meters, and then it will decay. So there will be no muons which are observed on Earth, right? But instead, what happens? The muon sees length contraction. So the actual distance between the Earth and the muon appears to the muon to be around this 660 meters, which gives it just enough time to reach the surface of the Earth. And the other way to see it is in terms of time dilation. In terms of time dilation, what happens? The muon's lifetime is delta T, but this is in the rest frame of the muon. So what is the lifetime of the muon as seen by the observer on the Earth? As seen by this observer, delta T prime is equal to gamma delta T, right? And gamma again is some very large number. It's approximately equal to it's more than 100, right? So this is greater than 100 times delta T. So the effective lifetime of the muon as seen by the observer on the Earth's surface, if you do the calculation, it comes out to be equal to something like 333, sorry, not 333. Well, it will be 2.2 microseconds. So it will be something like 10 to the minus 6. Let's just write it as 100, 10 to the minus 4 seconds. So you can write this as 0.22 milliseconds. So now the muon has 100 times as much time left to reach the surface of the Earth, right? And this is a direct test of length contraction and of time dilation. And even as I'm talking to you, muons are being created at the atmosphere, and they are reaching the surface of the Earth. And some of them might even be impacting into the environment around you. And the only reason that they are able to reach the surface of the Earth is because of relativity. If relativity was not valid, then muons would decay nearly 100 kilometers above us. They would never reach us. Okay, so I'll stop here for today, and hopefully I'll be able to figure out that derivation of length contraction, and I'll give it a better treatment in the next class. And the next class will be, today is Thursday, next class will be on Monday. Okay, so I'll see you then.
Sir,
Questions? Yes.
then if we say that if any particle which moves at c, velocity of the light, it seems that every length is like 0. It moves to, is it, sir?
Right. So it effectively everything appears frozen, right? To the observer moving at a speed of light, everything outside that observer's frame of reference, it appears to have shrunk and become very small, and also the time has become very large. Time intervals have become large.
Yes, sir.
So everything appears to be almost frozen.
Almost.
Right? And because if you have a massive particle, it takes an infinite amount of energy to take
Move
that
it at
particle
c.
to this, move it at c. And that is something that we'll look at in the next class. Okay.
Okay, sir.
So we have 4 more classes. In the next 4 classes, we'll talk about relativistic momentum. We'll talk about the mass energy relationship and relativistic energy. And I think that will cover our relativity syllabus. Okay. Questions?